for these two topics together. Okay, and let me introduce for you now chapter 7. In chapter 7, what we will say here, mainly we are talking about work and energy. Let me get rid of one of these, because this is gonna be less images. Okay, then we are going to talk about today work. Okay, this is one thing, one physical quantity, and the other one is kinetic energy. What I will talk about today all are scalars, which is gonna make it maybe a little bit easier. Now, we have studied in the previous chapters the force, and we were talking about like how force is changing the motion and how force is determining the quantity that is gonna govern the motion. Now we are going to talk as I said in this section, about energy as and momentum, and we are going to use them to describe the motion as well. You will find that we, in this chapter and the following chapters, we will develop a new method of solving, and that is going to be maybe sometimes easier than using forces, because we are dealing here with quantities that they are really scalars. Now, something we need to know that in physics, conservation laws are very important. We have conservation of energy, we have conservation of linear momentum, which is going to be the things that we are going to study, but there are other types of conservation laws, like conservation of angular momentum, what we will study also. But also in other fields of physics, you will find conservation of charge, conservation of, I will say, energy mass. There are many conservation laws that they are really very important. One of the concepts that is really so related to energy is work. And we will talk only today about linear motion. We will not include any rotation in this chapter, and we will talk about chapter later, about rotation later. Okay, then the first thing we are going to do is we are going to calculate the work done by a constant force. Then in the first part, you're gonna see always that my assumption is my force is constant, or I am talking about the average value of the force. And we will develop, like using kinematic equations, we will provide, I would say, develop an work energy theorem that we will use in this chapter. And then we're gonna move to something and say, what if my force is not constant? It is variable. How can I calculate the work done? And then finally, we're going to go and calculate power. Now, the work done by a constant force is here the idea of work. It has to do with two things. One of the things is I should have a force, and that force should lead to a motion. Then these are the two things that I'm looking for when I will talk about work done by a constant force. Now, I will say here, also, it's very important to know what is the amount of the force in the direction of the displacement. And this is the reason why here I will have the angle is gonna start making a difference, or is gonna enter the formula. Then I will say, since I am looking for the force that is parallel to the displacement, okay, I'm gonna make it general, FD cosine theta, F times D times cosine theta. And I want to bring to your attention here that this theta has nothing to do with the positive x-axis and our definition to the angle when we were talking about, like, adding by components. This theta here, it's gonna be between the two vectors. Then I need here always to draw the force vector and the displacement vector and find what is the angle between these two vectors. Based also on this formula, work is force times displacement, we are going to find that the unit used here, it is in newtons times meters, which is joules. And of course, it is abbreviated as a capital J. Of course, appreciation for Mr. Joule. Now, here in general, actually, this force, it is acting an angle on this suitcase, and this is the reason why we will say it is, we need to find the component of the force in the direction of the displacement, which is going to be F cosine D, F cosine theta, and then you multiply it by D to get the work done. Actually, what we need to know, maybe, and this is going to be like in upper levels of physics, like for 201, that there are two basic types of multiplication in physics. One of them, it is called the dot product, and that is the one here used for calculating the work. And always the dot product is gonna yield S a scalar, and its magnitude, it's FD cosine theta. Then from that here, we know also that work is a scalar quantity. Then we don't need actually to have a direction for it, just the unit. Now, okay, based on this formula, I want to maybe add another page here and talk a little bit about like how really the force and the displacement directions, they're gonna affect relative directions, they're gonna affect the work done. And I will use the black for force and the red for displacement. Okay, I don't worry now about the directions. Now here, I will say they are in the same direction, and then when they are in the same direction, theta is 0, and then the work done is gonna be the maximum. Why the maximum? Because cosine 0 is 1. As the angle is changing from 0 to just before 90, before 90, I will say 0 to theta less than 90. Here, the work is gonna still be positive, but it will decrease by increasing the angle. Then if you have more angle, you are going to decrease the work done. Now, finally, there is a situation where we're gonna have the force, and this is the displacement. This is when theta is 90, cosine 90 is 0. Then the work done here, when the angle is 90, is gonna be 0. Now, between, okay, then let me mark these, like this is the first, and then here I said this is the second, this is the third. Number 4 here, it is the angle greater than 90, but is gonna go to let's say the maximum is gonna be 180 here. And I will say whenever we are going to find the cosine here for, let's say, if you have 120 is gonna be negative, then here cosine theta is gonna be negative. Okay, and I am very interested in the case when, and then the work done is negative as well. Okay, I'm interested in a case when I have my object, this is the direction of the displacement, but it is experiencing force of friction. Then now here theta is 180 and cosine 180 is -1. Now, maybe earlier I mentioned that work is a scalar quantity. Then what does it mean to be negative? This means that the energy of this system is going to decrease, or like the system is going to lose the energy. And I will say, when I will say lose, it will not lose. It will maybe donate it to something, to like the system, the environment, whatever it is. But the energy of the system is gonna decrease, and we're gonna talk about that. And I will say here the energy is dissipated. And what does it mean, dissipation? Dissipation means that the energy is gonna be converted into other forms that we cannot reuse again. Now here, if the force is perpendicular to the displacement, this is the situation. You are, and I will say here, you are only carrying, you are not lifting. Okay, remember, carrying means you will not move it up or down. Just you have it, you have applied that force, which is it's gonna be exactly equal to the weight, and then you will move straight horizontal. All right, then here no work is done on this grocery quantity. The force he exerts has no component in the direction of the motion, and this is the reason why the work done is going to be 0. Okay, this is again talking about what I have introduced, that the work done is FD times cosine theta, and if theta equals 0, then cosine theta is 1, and W, the work done, is F times D, because cosine theta is 1. And here are the different situations where I was talking about when the work is going to be positive, when the angle is less than 90, at 90 is going to be 0, and then between 90 and more than 90 and to 180, the work is going to be negative. Is it possible to do work on an object that remains at rest? No. Why? Because we said we should have force and we should have motion. Then if you are, let's say, hitting the wall, okay, and the wall is not moving, okay, then the work done is 0. You have force, but you don't have any displacement. Then also here, based on our definition, Work requires that a force acts over a distance. If an object does not move at all, there is no displacement and therefore no work done. Now for the conceptual question here, number 2, a box is being pulled across a rough floor at a constant speed. What can we say about the work done by friction? Okay, here the work done by friction is gonna be negative because remember cosine 180 is negative 1. Okay, friction acts in the opposite direction to the displacement, so the work is negative, or using the definition of work here, maybe it's a little bit, okay, misleading, then I will say is gonna be FD cosine 180, and that is gonna be negative FD. Now here, friction and work. Also, this is a conceptual question. Can friction ever do positive work? Yes or no? Yes, because we can have sometimes, let's say we have a pickup truck, and then you are, you have a box in that truck. Then if the box moves along with the truck, then it is actually the force of friction that is making the box moving. One of the situations that very interesting is when I have, let's say, a satellite in its orbit, or anything that is doing centripetal motion. Work done by forces that oppose the direction of motion, such as friction, will be negative, and the centripetal forces, they will do no work because they are always perpendicular to the motion. Now remember, for any here point, the direction of the motion, or the displacement, the direction of the motion is the direction of the velocity tangent, and the force is centripetal, then it is to the I would say it is towards the center. Then now this is 90 degrees and cosine 90 is 0. Okay, now here another situation. A ball tied to a string is being whirled around in a circle. What can we say about the work done by the tension? Of course, doing no work because cosine 90 is 0. No work is done because the force is perpendicular to the displacement. Now, what if I have more than one force? Okay, when I have more than one force, I need to calculate what is really called, what is called the total work. Okay, then work total is gonna be the work done by all the forces acting on the object. Now, here are two approaches. Either you will find the F net, then you are going to work with Newton's second law. Find what is sigma F, and then you're going to say W is F net times D. All right, and this is gonna be your work total or net. The second approach, which usually I like to do it, okay, because I don't want to go back to maybe working with the Newton's second law, although I need to draw again free body diagrams, I will find the work done by force 1, which means it is F1 D1 cosine theta 1. And I will do the work done by force 2 F2 D2 cosine theta 2. And then the work total is going to be the work done by force 1 plus the work done by F2 plus the work done by force 3, and go on. Just I want you to remember here that why I like this approach here also, because you're gonna eliminate if you have a force that is perpendicular to the displacement, then the work is 0. And of course, if you have the F and D, they have 180 degrees, this is gonna be negative. Then like finally what you end up with, either adding or subtracting, which is gonna be very straightforward. Okay, but the two approaches are okay, and if you like to use any you like, it's okay. Now also I want you to know that lifting a box is different from carrying a box. Okay, then when you carry is different from you lift. Okay, lifting means that you will get, okay, the force up and the displacement up. When I am talking about carrying, okay, the force again is gonna be up, but my displacement is gonna be horizontal, which means 90. Then here I have theta equals 90, and this leads the work equals 0, whereas here the work is F times D. Now, if you lift a book with your hand in such a way that it moves up at constant speed, okay, while it is moving, what is the total work done on the box? Now, here we are talking about the total work, and we are talking about a situation when I have my book is moving with constant speed. What does it mean, constant speed? That the lift force should equal mg. Okay, and then the work done by gravity is gonna equal the magnitude of the work done by, let me add a page here. I wanna add a page. All right, then here, okay, I have, this is mg, and this is the F lift. Okay, now if I wish to calculate work of F lift, remember the force of lifting here, okay, constant speed means sigma F equals 0, then F lift should equals mg. Then it's gonna be mg and times d cosine 0, because I am moving the object, the displacement is upward. Then here is gonna be mgd. When also the work done by mg, which is the weight, mg times d, but now cosine 180, because you are moving the object upward and the weight is acting downwards, then this is going to be negative mgd. And then we are asking in this question about the total. Then this is mgd minus mgd, and it should equal to 0. Okay, also we added here a comment that because we are going to introduce something, is that what is really the change in the kinetic energy of the book? It is 0 because it said constant velocity, but we did not yet talk about how we calculate the kinetic energy. Okay, but just I think maybe here it's a good point to define the kinetic energy as 1/2 mv squared, and okay, the change always is gonna be final minus initial, and since it is the same velocity, then it is 0, the change. And we will see later that we will relate kinetic energy to work done. Okay, this was introduced also before, that it is the dot product, but just as I told you, maybe for this course we did not talk about the different types of multiplication, and this is what we should do in Physics 201. Now, also something that you need to pay attention to, the differentiation between work done by the object or on the object. Okay, now make sure you note if work is done by an object or on an object, and also note which force or net force is responsible for the work done. Okay, so that of course relate every work the force to the displacement and the angle between the two. Now, solving word problems, we will draw free body diagram. I told you this is needed because either I will use a Newton's second law to find the net force, or I need to know what is the direction between each force and the displacement. Choose a coordinate system. Apply Newton's laws to determine any unknown forces. Okay, if we have unknown forces, find the work done by a specific force. To find the net work, either find the net force and then find the work that it does, or find the work done by each force and add. Okay. Now I will say, starting this week, like all these like problems that try using it, you will find them recorded separate by a page. I will add that page to the module, beside of course my solution while I'm doing the lecture. I'm gonna give you an opportunity that maybe instead of going over like the whole recording once, twice, 3 times, or whatever like you are looking for, you can have these problems just recorded by themselves. And I like here to thank Janet for sharing her material with me. We are planning also actually to have all this material completed, and all these videos uploaded for all the students that we teach in our department. All right, here you push an 18-kilogram shopping cart at constant velocity 15 meters down the aisle, and always I want you to pay attention to if you will find this description or not, because this is gonna mean so many things. you are exerting a force of 12 newtons at an angle of 20 above the horizontal. What is the work done by each force? Okay, now I know that since I am talking about constant velocity and there is constant velocity motion, I know that I should have also, which what was not maybe mentioned, that I should have force of friction. Then I will draw the free body diagram. I have the normal force, I have mg, I have this is the force applied, and I have the force of friction. Now the work total is gonna be the work done by the normal plus the work done by mg plus the work done by the friction, the force applied plus the work done by friction. And these all, they should add up to 0 because my object is not actually, is not accelerating, or it's moving with constant velocity. Okay, based on this, the work done by friction, I can calculate that as Fd cosine 20. How can I find the force of a friction? This is the force. I'm confused a little bit here. This is the applied force. Okay, and the applied force is 12 newtons, and the object is moving. Look here, I'm looking for displacement and force. This is the force and this is the displacement. The angle between them is 20. Then I will say 12 newtons times 15 meters cosine 20, and this is really the work done by the force of the applied force. For the sake of significant figures, I round it to 170. I know since the total work done should be 0, then the work done by friction is going to be force of friction here is going to be, let me write this FF here so that you will not be confused. Force of friction. Force of friction, of course, is going to be also F. Force of friction is going to be F times cosine theta. Okay, from the setup here, because the object is moving with constant velocity, then F friction should equal to the component of the force in the direction here. I did apply sigma Fx equal 0, and then I have F cosine theta minus FF should equal 0, and then the force of friction is going to be, okay, the F cosine theta, which is 11.3 in newtons. Work done by friction will equal that FF here times d cosine 180, and it is negative 170. We can verify that again, that the work done is going to be 0. 170 minus 170 is 0. We have here another one. A block of mass 2.5 kilogram is pushed 2.2 meters along a frictionless, okay, then we don't have friction, by a constant force 16 newtons, force directed 25 degrees below the horizontal. Determine the work done by the applied force, the normal force exerted by the table, and the force of gravity, and the net force on the block. Then the first thing, as we know, is we should draw free body diagram. Then I have, this is the force applied. I have this is mg, the weight. I have this one as the normal. And I don't have any, I will say, frictional forces. The work done with the applied force is F, oh, F times d cosine 25, and that is 16 times 2.2 times cosine 25. Don't use here negative 25, okay? I said that that is the angle between the two vectors. Then you're gonna take its value. And this is 31.9. The work done by mg, which is the work done by the weight, is gonna be 0, because if you look at the displacement vector, let me put it in green here, D. Okay, if you look at it, it will be 90 degrees. Also, the work done by the normal is again 0, because the 90 degrees rule. The work done by the net, okay, the net force on this object is gonna be F cosine 25, okay, times D times cosine 0, which is 31.9. Because this is the net force on the object. Like, I can simply say, if this is my free body diagram, I will have here mg, and also I have here the f sine theta, and here I have the f cosine theta, and I have the normal. Okay, now the like the n for d, it is in this direction. Okay, now these f sine theta and mg, both of them, they have 90 degrees, then they will not do any work. And the normal also is not gonna do any work. The only force that is gonna do work, and the net force on the object, it is F cosine theta. Because normal here equals F sine theta plus mg. Now, what if the force that I am dealing with, it is variable? It's not constant. Then I will say we are going to deal with another approach. This diagram here, it is representing this like a graph. It's not a diagram. This graph is plotting here force versus position, and that one, it is in when the force is constant. Look here, the force is not changing. And we will say, of course, this is from calculus, but we will not deal with any calculus. If you have FD graph, I will say the area under the curve will equal the work done. Okay, and we are going to use the we will use that rule here. Then if you have a very complicated, let's say, graph, you will dissect, you will make this graph different. You will cut it into different portions that you will be able to find the area under the graph, and then you will say this is A1, this is A2, this is A3, this is A4, and then the work total is gonna be the A1 plus A2 plus A3 plus A4. Again here, if it is it's gonna be like maybe more complicated, you might have also, I will say, not only rectangles, you might have also triangles. If I want to be very specific, for example, here, I might have a triangle. And for the triangle, the area, it is 1/2 base times height. Remember, like I want you, because we will use the area under the curve for more than one thing. It's not only for the work, we can have it also for the impulse. Later we will talk about this, okay? Now, of course, as I said, this is from calculus, and in calculus means it is integration, but we will not do any integration in this course. Now, one of the examples on the work done by a variable force, it is the force of spring. Because the force of spring, it depends on the stretch or the compress in the spring. Then I will say this is going to be a variable force. Okay, this is here, Hooke's law. It is presenting for me the relation between force and position. And it is in, this is of course part of the graph. This is when it is in the elastic region where Hooke's law can be applied, then it's going to be a straight line like this. And if I wish to calculate the work done in stretching the spring, I would say it's the area under the curve. And I did use here the area of a triangle. Sorry, A, it is 1/2 times the base times the height. And for the base, it is x, and for the height, it is kx, and this is 1/2 kx squared. Okay, now most of the time I will say we will find situations, especially in the coming chapter, where we will work with conservation of energy. We will work with the springs. Then I will say, what if we have a situation where we have a spring, then we need to deal with that spring and find what is really the energy. Okay, if it takes 180 joules of work to compress a certain spring 0.15 meters, what is the force constant of the spring? This information was provided for us just to calculate K, and then W here, we know it is 1/2 kx squared. We spend 180 joules of work, then it is 1/2 K times negative 0.15 meters. Here, because it is compression, if it is stretching, because usually we will assume something like this, then okay, we will say compression means the displacement is going to be in this direction. And we will find K as 1.610 to the 4. Remember, K, it should be always a positive number. Now, to compress the spring an additional 0.15, does it take 180 joules, more than 180 or less than 180? Verify your answer with the calculations. Now, I will say, in order for me to compress an additional 0.15, then I will say my initial compression was 0.15 meters. And for the second one is going to be an additional, then it's going to be 0.3 meters. And then I will say, in order for me to go from the 0.15 meters to 0.3, I need to calculate the work done as 1/2 K x2 squared minus 1/2 K x1 squared. And then I will plug in my numbers, and you will find that it is the work done in compressing the spring an additional 0.15. It is 540 joules. Then it is more than 180. Don't think that is gonna be the same amount, okay? Because the nature of the equation. Now, here we are going to add the concept of energy to this topic, and I will say here we will talk about two types of energy. We will deal with kinetic and potential energy. There are more than one type of potential energy. Like actually the potential energy means like it is the energy stored in objects, and energy can be stored in many like using different ways and different types of energies. But like in this chapter we will talk about only kinetic energy. Something that I want you to know, that the kinetic, we use K for the kinetic. For potential we use U. K plus U equals something, we call it E, which is the mechanical energy. Okay, now in this chapter, as I mentioned, we will talk about mainly kinetic energy, but we might, and we did like mention something related to work done by spring, which is going to lead us to talk a little bit about elastic potential energy. Okay, now when positive work is done on an object, its speed increases, and when negative work is done, speed decreases. We can actually derive a relationship that is going to verify this, and I will say using Newton's second law and using also kinematics. We can actually find that the work done, it is F net times D, and then F net, it is mass times acceleration times displacement. From kinematics, we have this equation, V squared equals V initial squared plus 2A times delta X. Delta X is my D. Then I will derive an expression for A, and then I'm gonna put it in this one, and then finally I will find that the work done equals 1/2 mv squared minus 1/2 mv0 squared, and that is the change in the kinetic energy. Something that I want you to know, that the work done, as we mentioned so many times, it doesn't need to be always positive. Then it might be negative, and the negative is an indication of a decrease in the kinetic energy of the system. Okay, we're gonna have so many situations where there is gonna be a decrease in the kinetic energy, and this means that we need to say that the kinetic energy of the system has been decreased, and what is really the the reason, because we have this type of collision. We will talk about this more maybe in momentum. Another thing that we will maybe we want to say here, it is just, this is what is called a translational kinetic energy. Translational means that the object is going to move from one place to another, because there are other types of kinetic energy we are going to talk about later. Work energy theorem means that the total work done on an object is equal to its change in kinetic energy, and this is the general equation that we have, and that one is W total, the total work done is change in kinetic energy. It is 1/2 mv final squared minus 1/2 mvi squared. Now, let me also continue with these solutions. On a frozen pond, a 10 kilogram sled is given a kick that imparts to it an initial speed that is going to be 2 meters per second. The coefficient of kinetic friction between sled and ice, it is 0.1. we are going to use the work energy theorem to find the distance the sled moves before coming to rest. Then the mass is 10 kilograms, the initial velocity is 2, and mu k is 0.1. And I will say here that finally that sled is gonna be going to 0 velocity, then this means that its final is gonna be 0, and I will have here negative 1/2 times 10 times 2 meters per second square is gonna give me negative 20, and delta K, the change in the kinetic energy, will equal to the work total, and that is the only force that is acting on that sled is friction. I mean like in the horizontal. Okay, then this is force of friction. Of course, we know that mg is here and normal is here, but these are not part of the work equation because they are perpendicular. Okay, the work done by friction, it is negative F force of friction times d, and from that we will be able to calculate what is really d. D is going to be just 2 meters for the sig fig. Of course, here I did show you that I have calculated the force of friction based on Newton's second law. Remember, we said that you might need to apply in Newton's second law so that you will be finding what are really the unknown forces, some of the unknown forces, because like in this question, we assume that we don't know that friction, we were asked to calculate the displacement, then we don't know the force. Okay, now we know that the PTs are really doing a lot of this physics when they are trying to analyze accidents. Then I will say at an accident scene on a level road, investigators measure the skid marks to be 88 meters long, and the accident occurred on a rainy day, and the coefficient of kinetic friction was estimated to be 0.42. Use these data to determine the speed of the car when the driver slammed on the brakes. Okay. Of course, here we have the situation where showing like all the forces on the car, and this is the minute I will say that driver has slammed on the brakes, and there is the force, the normal force, the mg, and the force of friction. Initially, the car was moving with v0 equals 0, that velocity that I need to find, and then finally it will stop. Of course, again, apply in Newton's second law so that you will find the unknown forces, because I want to find what is the work done total, because the only force that is gonna be in the x direction is going to be the force of friction. Minus mu k times the normal force times d equal change in kinetic energy, and the PTs, they are dealing with this type of equation to determine what was really the speed of the car initially. This is here is the work done by friction, and this is the change in the kinetic energy. From that, we can find that 26.9 is the initial speed, which is about 27 meters per second, which is about 60 meters per hour. Now, one thing that I want you to know here is this is the skid marks, 88 meters, and I will say why does the car's mass did not affect, because if you looked here you will find that the mass from the left and the right, they will cancel. Now here I will say we're going to have our exiting ticket for chapter 7 presented here, and I will say, what if the car was moving with 2v0 instead of v0? How this is gonna affect how this is gonna be affecting the skid marks on the road. Okay, then I want you to find now if the velocity of the car was, instead of being v0, which is the 27 meters per second, what if it is 2v0? How this is gonna affect the skid marks? And here I want you to find for me the ratio, okay, between the skid marks distance for 2v0 divided by the skid marks distance for v0, and give an advice for drivers. Then your I will say your assignment for this one is gonna include calculation that is gonna bring for me that ratio here, and then the advice that you are providing for drivers. Okay, here we are just having a the work thing applied to free fall. 2 stones, one twice the mass of the other, are dropped from a cliff just before hitting the ground. What is the kinetic energy of the heavy stone compared to the light one? Now, the kinetic energy, it is based on, I will say here, it is based on the mass and the velocity. And because the velocity is going to stay the same, but since the mass, one of them is double the other, then the heavier is going to have twice as much. Because remember, the kinetic energy has to do not only with the speed, it has to do with the mass as well. In the previous question, I will say, just before hitting the ground, what is the final speed of the heavy stone compared to the light one? Okay, we know this is from free fall, the speed is going to be the same because the acceleration is going to be the same for both. Is it possible for the kinetic energy of an object to be negative? Of course, no, because the mass cannot be negative, and the speed, even if it is negative, is going to be squared, then always is going to be positive. Now, power, it is another concept related to this chapter, and it is a measure of the rate at which work is done. Then P, it is work divided by time. Then it is related to how fast work is done. Okay, it is joules per second, the unit, and we say it is watt. There are 2 expressions. This one here is going to give you the average power, and this one here is going to give you the instantaneous power. Then it can be F times V, power F times V. We're doing here one of the problems. While running, a person dissipates about zero point 0.6 joules of mechanical energy per step per kilogram of body mass. If at 60 kilogram person develops a power of 70 watt during a race, how fast is the person running? We're gonna assume that the running step it is about 1.5 meters long. Now, I want you here to organize your work. When I will say 0.6 joules per step per kilogram, like I can write this as this. Okay, and I will say the work total is gonna be that small or that rate of the work multiplied by the number of steps which I will use for it n, and this is the mass. Then in order for me to calculate what is the total work, I will say 0.6 because it depends on how many steps I'm gonna make, and it depends also on my mass. Okay, then 0.6 joules divided by step times kilogram is gonna be times n, which is the number of steps which I need to find, times 60 kilograms. Then the work is 36 joules per step times n, which is the number of steps. Then the power here is going to be W divided by time also, and I have the work. The total power was 70 watts. The total work, it is 36 joules times number of steps divided by the time. Then I will be able to find how many steps I am making every second. It is 1.9 steps. But of course, steps, they are not maybe our unit for measuring distance. And this is the reason why we need to convert this into meters. Then I will say 1.5 times 1.9 is going to give me the total distance. When I will divide this by the total time, which is, in my case, it is 1 second, is going to give me the total here, distance divided by total time, and it's going to give me 2.9 meters per second. Okay, another problem here related to power is I am talking about a shot putter accelerates a 7.3 kilogram shot from rest to 14. If this motion takes 1.5, what average power was developed? We know that power has to do with work and time, and also the work has to do with the change in the kinetic energy. Then always when you are going to notice that you have a velocity and you have two velocities and the mass, then you need to find what is really the change in the kinetic energy. The change in the kinetic energy here equals the work, and then we were able to calculate the work done as 715.4 joules. And then the power, it is the work done divided by the total time, which is 715.4 divided by 1.5. And this is going to be 4.810 to 2 watts. I put my number in this notation so that my answer will be consistent with the rules of significant figures. Now, Mike here performed 5 joules of work in 10 seconds, and Joe did 3 joules of work in 5 seconds. Who produced the greater power? What you need to do is you need to calculate the power in both cases. And this one, 3 joules over 5 seconds, this is going to be 0.6. And that is going to be 0.5. And that one is Joe's. Then Joe did or produced more power. Yeah, this is a simple calculation. Engine 1 produces twice the power of engine 2. Can we conclude that engine 1 does twice as much work as an engine 2? We cannot unless we know the time, because the time is the one that is also a key factor in calculation power. Which contributes more to the cost of your electric bill each month, a 1500-watt hair dryer or a 600-watt microwave oven? Of course, again, we will not be able to tell until we know what is really the time for using that microwave and that hair dryer. Then depends upon how long each one has been used. Okay, this is the summary of chapter 7. If the force is constant and parallel to the displacement, work is force times distance. This is the general formula for it. What if I have more than one force? And then the units for work and energy is joules, which is in newtons times meters. And the total work can equal the change in the kinetic energy. And we have defined the kinetic energy. Now, work done by a spring force